Okay, so integration by parts will reverse the product rule, and we use integration by parts when you have a product of two functions, like integral of x cosine x, or integral of 3x e to the 2x powered. So anytime you have a product of two functions. Because, as we learned, that goes back to that, I don't know if I did the division rule or multiplication rule in your version of the test, but it was that multiple choice where, what the properties of integrals, there is no property that says the integral of x times cosine of x is the same as the integral of x times the integral of cosine of x. You can't do that, nor can you divide them. But this will handle a product of two functions. So if you just go ahead and box this guy, write it on the top of your notes. This is the integration by parts formula. We use this formula with the product of two functions and no u du substitution properties. We have had some functions that were products, but we had the u du thing going on there, whereas in this case you won't be able to do a u substitution directly. Any questions on that? All right, so let's start with an example here. We have the integral of x cosine of x. We could not use a u substitution on this because if I let x be u, the derivative would be 1. That's a problem. If I let cosine of x be u, then its derivative is not x, so that's not going to work. So the idea here is we're going to make a little 2x2 table. We're going to let u equal one of these functions. We're going to let dv equal the other function. And then we're going to calculate or find du and then also find v. So it's really trial and error. I'm gonna actually have you do a little exploration into, how you can decide what are good choices of u versus dv. But in the formula, if you look at the formula on your sheet, for the formula, we need to know u, we need to know v, and then we also need to know du as well. So those three things we need to know in the formula to use the formula correctly. So we need a guess here for what u might be. Does anybody have a suggestion for u? Any idea on what? Probably not at this point here. Let's do this. We have the integral of x cosine of x is equal to, I'm going to go ahead and let u equal x in this case. And then dv will equal cosine of x. And I need to add a dx here. So the derivative of u would be just 1 dx, and the integral of cosine of x will be sine of x. That's right. So now I have everything I need for the formula. Now the idea here is the same as it was with u substitution. That is, we are going to rewrite this integral in such a way that we have what's left can be integrated from something on the table. It makes sense that this was number 1, I guess, because it's another, I guess, rewrite. And so, although you have to know all the other integrals before you can do this one. So we're trying to match it up with one of those. So according to the formula, it says you take the product of u times v. You'll see u and v right here at the diagonal of this little 2x2 table. So u times v would be x sine of x minus the integral of, so it's u times v minus the integral of v du. So v is sine of x, and du is just dx. So do you see what happened to our original integral here when we applied the formula to it? Not really. Look at this integral here. How's it different from this integral besides that being a different trig function? Yeah, we no longer have a product. There's no x there. As a matter of fact, we can integrate this. It's easy to integrate it. It's one of the values on your table. So this is x sine of x. And what's the integral of sine of x? Negative cosine of x. So negative is going to make it positive cosine of x plus c. So if I have integrated this correctly, what should I be able to do with this integral? Take the derivative and get back to this. Try that right now, please. Go ahead and take the derivative using the product rule. Take the derivative of this thing using the product rule. Try it right now. So yeah, copy down example 2. You're going to want to integrate x cubed e to the negative 3x dx. What's your guess as to what you would be? X cubed is a good guess based on our exploration we just did.
Yeah, I would say x cubed.
X cubed. Now, let me just get a little more space here. I'm going to go down here. You don't need to write this down. I'm going to end up erasing all this. So just reason through this with me. So I let u equal x cubed. So du would equal 3x squared. dv is equal to e to the negative 3x. What's v? I'm going to integrate this thing. Now we're integrating, so it'll be divided by. If you're differentiating, it would be multiplied by. That's the only difference. Trig functions, cosine and sine, work the same way. You just take the integral, whatever the appropriate integral is, and then divide by the derivative of v and sine. Okay, good. So let's go ahead and apply the formula. So this is equal to u times v. So that would be negative x cubed e to the negative 3x over 3 minus the integral of v du. So v is this thing. So that would be negative e to the negative 3x over 3 times, so I said v du, 3x squared dx. Now, we've got a little bit of a problem here. It's actually not a problem. It's just a lot of work. Did I improve my situation? It's questionable. I actually did improve my situation because I have moved from x cubed to x squared. My next move at the next iteration of this integration by parts would bring me to x to the first, and then my next iteration would actually get me to my answer. Good, you're seeing the problem with that. So somebody figured out a way, okay, they took this and they said, hey, there's a pattern here. There is a pattern. There's something going on here. I could keep doing more iterations of this, or I can see, hey, there is a pattern. We have this product of u times v minus the integral of v du. Then I'm going to do that again, create another u times v, if you will, minus another integral of v du. So what happens is you have several products here. Can you tell me how many terms my final answer will have based on this? You have to think about it a little bit. Here's one term. I produced one term. What's this going to do? Oh, you didn't think very long. Okay. No, you're right. Converge, yeah. Kevin's saying, do you guys see how there might be 4? I'm gonna create another one when I'm gonna go down one power, create another one, and then down one more, and then create 2 from that. So I will have 4 terms. So, somebody, I don't know who's to attribute this to, but tabular integration is a great way to do this. As a matter of fact, you could use, and I've had students use it, tabular integration on every one of these, because essentially I created a table up here in green. This is a table. So I would just need to extend it, I think, one more piece here. But the table looks like this. You can go ahead and copy this down now. We're going to use tabular integration on this and save doing multiple iterations of integration by parts. If you only have to do one application or iteration of integration by parts, maybe 2, then go for it. But if it looks like it's going to be more than that, which is happening when we have a higher degree polynomial times an exponential, or if it were times a cosine or sine, it would be the same deal. So we're still going to let u equal x cubed. I have f and its derivatives, g and its integrals, so we're going to, f is our u actually, and g is our dv. So u and its derivatives, so we're going to label x cubed as our u, and we're going to label e to the negative 3x as our dv. And we're going to go ahead and find the derivatives of u all the way down to 0. So the first derivative here would be 3x squared. Second one would be x. Third one would be, and then 0. So you know you can stop when you get to 0. And then here we're going to find integrals. This will be a little more work. But the first one we already did. It's e to the negative 3x. I think I better write it this way. Try to fit it in here. E to the negative 3x divided by negative 3. So you can read that. E to the negative 3x divided by negative 3. What's the next integral going to be? E to the negative 3x divided by positive 9. Good. Because I'm going to match it, and then divide by negative 3, making this bottom positive 9. And then the next one will be e to the negative 3x divided by negative 27. And then the final one, e to the negative 3x divided by, but you've never seen fractions with 81 on the bottom. Or 27 for that matter. So, yes, we have u and all of its derivatives and g and all of its integrals. And if you notice in the formula, I erased it here, but we can look up this one up here. Look at in the formula, we have minus the integral of whatever. So because of this minus sign, what's going to happen is the first product will be positive. So my first product will actually be x cubed times this. We saw it when I kind of started that problem earlier. So this will always be positive, and then because of the minus sign in the formula, the next product will be negative. So you have to take the opposite of whatever the product is.
So it always goes down one step.
It always goes down one step because this one we were just using this for our dv, and remember the first product is u times v, not u times v. So it's going to go down here and then here. And we're going to alternate signs. So it's plus, minus, plus, minus. We are going to alternate signs. Do you see why we're alternating signs? I think that'll help you to remember. Maybe somebody could explain here. Just based on this example, why are we alternating signs? Okay, the first uv was obviously positive, right? The formula says u times v. There's no negative sign in front of it. But after that, yeah, we have this negative sign to distribute. So when I create a uv minus integral v du out of this, I'm going to have to subtract the uv. And then for the next time I do it, I'm going to subtract the negative, and so it's going to make it positive. So alternating signs all the way down, and that comes from the formula. Okay, so my final answer, watch this. Just using the table, doesn't even look like integration here. The integral of x cubed e to the negative 3x dx is equal to the product of these two, which is negative x cubed e to the negative 3x over 3. Okay, I got to watch my signs here. The product of these two is positive, but then I have to subtract it. So it'll be minus 3x. Well, we could simplify 2. Should we simplify in the same step? Would that be okay if I did that? No? Yeah, okay, I better not. 3x squared e to the negative 3x over 9. If you'd like to simplify, you can. This is going to end up being 1/3. And then finally here, 6x times this. So we have a negative and a negative. So let's see. No, negative and a positive, huh? So 6x times this. We have a positive here, but the product is negative, so it'll be minus 6x e to the negative 3x over 27. And then minus 6 e to the negative 3x over 81. After all that's done, don't forget your plus c, or minus 1/2 for you. They all end up being minus just because the ones that have the minus sign as the sign are positive products. So we're multiplying these arrows mean multiply these two together. It's the UV part of the formula. So clean this up a little bit. It's negative x cubed e to the negative 3x over 3 minus x squared e to the negative 3x over 3 minus 2x e to the negative 3x over 9 minus 2e to the negative 3x over 27 plus c. So you're right with the 4 terms. And do you see how this tabular method, you could use it in every problem? How could you extend this tabular method to this problem up here? What would you have to do? Here we have this. What do I need to add in? Or do I need to add anything? Units, derivatives, dv units. Look at what the final answer was here. So here's the x sine of x. Then it would be, I want to end up somehow with the last thing here. Remember, this would just be 1. We could, or we could just integrate one more time. So if we integrated one more time, we would get one more integral here. So the integral of v would equal what? Negative cosine of x, right? And then when I draw in this little diagonal arrow here, remember this would be plus and this would be minus. Minus, minus would change it to positive. So I would only be listing x and then 1 and then 0. And here I would have cosine of x, sine of x, negative cosine of x. And you could use tabular method on that one. So it's just doing u and its 2 derivatives and dv and its 2 integrals, and that would take care of it. That would be the minimum you would do. So tabular method will work on any of these. All right. Any other questions on this? One more example here. Throw a curveball at you. With the integral of e to the x cosine of x dx. Now what? What are we going to let be our u? What are we going to let be our dv? Choose wisely or we'll have to start all over again. You might want to wait to take the notes of this. Who should we make responsible? You want to be responsible? Who wants to take a guess? Third period, Isaac Reynolds took the guess and he guessed why. And if he had guessed, you know, it's a 50-50 chance. They would have been pretty mad at him if he had not guessed perfectly. We would have gone through a couple iterations and then realized, wait. The goal here, you might want to think about this a little bit before you guess. We're going to choose our u and our dv, keeping in mind we will not be able to take the derivatives down to a constant like we could before with the polynomial. But we will need to end up with a term that matches this one. I'm not going to tell you why yet. I'll show you the algebra behind it. But we need to end up with a term that matches this one eventually. So you can really use this, like my first example I did here. It's a good way to look at it. You know, see what's happening here as I integrate now. So whoops. So we eventually need to get back to we need to get a term that's e to the x cosine x here. But you have a guess for you? Anybody want to take a chance? Yeah, I'm just gonna make some moves. You're gonna let u equal. Oh boy, I'm gonna do 2 different things. Integral of e to the x is just e to the x. So what do you want? I'm hearing 2 different things, so we're going to go for Kevin.
I like that.
Okay. we like to keep drill.
Not good with that.
So what do you want, Kevin? Cosine x for. He's getting threatened already. All right. So here we go. Derivative of cosine of x. I would wait to write this down. So derivative, I'll leave it up here. You can copy it down after we figure things out. So derivative of cosine of x is. Oh, okay. Yes, negative sine x. And then integral of dv, my favorite integral. Even I can remember this after summer break. So e to the x. So here we have integral of e to the x cosine of x equals u times v. So we have e to the x cosine of x minus integral of v du. So we have, let's call it, how do I want to write it here? Negative e to the x sine x. Let's write it. Let's keep the negative sign in there. And then we want it, and then dx. So it doesn't match that yet. So we're going to have to do another iteration here. I think I will go ahead and change my signs over if that's okay here. We're not copying it down here. So we have e to the x cosine x plus. All right, so if we're going to go with the same theme, making the trig function the u and the exponential function the dv, my next iteration would look like this. U would equal sine of x, and dv would equal e to the x. So du would be cosine of x, and v would equal e to the x. All right, we can't use the tabular method. That's only going to work if it reduces down. Yeah. So the tabular method is not going to work here. This is an example of a mixture of two transcendental functions. So we have plus the integral of e to the x sine of x dx, and my new, I'm going to shoot red right now. Oh, I forgot, I got to put my uv in before you. So plus, so u times v would be e to the x sine of x, there's my u times v, minus the integral of, Kevin choose wisely, v du, Kevin chose wisely. That's what we have so far. So I didn't tell you completely why we needed to match the left-hand side, but you see why now? Can we solve for the integral of e to the x cosine of x dx now? Can we solve for that? This is strange algebra. This is algebra with integrals, right? Like nothing you've ever seen before. But what happens if I take this and add it to both sides? How many of these do I have?
Those.
2 of them. And then what do I do with the 2 to get rid of it? Divide. Yeah. 2 more steps. It's algebra 1. So we're going to add the integral of e to the x cosine of x dx. This is one of the biggest things in, this is what they're trying to focus on more with Common Core, which they are correct. It's helping students to see algebraic forms. This is just an algebraic form. That's all it is. It's 2 smiley face. You're about to get 2 smiley face. Equals something. And we solve for smiley face by dividing by 2. So I have 2 smiley face equals e to the x cosine of x plus e to the x sine of x. So there I am. Remember, the goal is to find the integral of e to the x cosine x dx. Can we do that? Sure. You divide each side by 2, leaving us with the integral of e to the x cosine of x dx equals e to the x cosine of x plus e to the x sine of x divided by 2. And after all that, don't forget plus c. Or you did all that and you'll still only get half credit, 50%. Yeah. So that's maybe in a 9-point scale you get 8 on that. But I didn't want to put in a C here because I'm going to divide C by 2 and then I have to look at C. That's confusing. Linda added a C on the